Hi everyone, my name is Zobaer and my group partner is Atik. We are going to present a paper from CVPR conference titled Zero Reference Deep Curve Estimation for Low Light Image Enhancement. So as you can understand from the title that this paper talks about enhancement of images that were captured under suboptimal lighting conditions. Here are a couple of examples of such low light images. You can see that both of these images are quite dark and lack aesthetic quality. Also, the objects in the darker parts, like here, actually can hardly be discovered. Thus, we get only insufficient information from such images. In order to enhance such images, there are quite a few techniques, including histogram processing, pixel level transformation, then spatial or frequency domain filtering, homomorphic filtering, and so on. Most of these were taught in our digital image processing course. However, there are some deep learning based methods too, which can be superior because deep learning or deep neural network can learn necessary parameters automatically for image specific enhancement. For example, there are two deep learning based methods using CNN and GAN are cited in this paper. But both of these techniques require paired or unpaired data to train necessary parameters. CNN-based approach requires paired image data, like one input image and one reference image for training purposes. GAN-based approach requires unpaired training data, which means it still needs reference images, but one-to-one pairing of data is not required. So in real applications, reference images might not be available, and the nature of enhancement required may vary a lot depending on the input image. Hence, the authors proposed a non-reference low-light image enhancement technique. That's what we will talk about in this presentation. The proposed technique is called zero reference deep curve estimation technique. So it does not need any reference image to compare with. Instead, it estimates pixel level transformation curves that are image specific, pixel specific, as well as higher order. It does so by using a deep convolutional neural network in an iterative way. So the authors evaluated the results by 4 customized loss functions, which my group partner will talk about soon. So because of the highly adaptive nature of the transformation, it was found to perform better than other conventional techniques in enhancing images with diverse lighting conditions. You can see an example here where this is a low light image and it has been enhanced by different techniques. So C and D are showing the results with conventional CNN and GAN that require paired or unpaired data. So C has the face area underexposed, as you can see, and in D, the background is to some extent overexposed. So even after enhancement, we're having these effects. But in B, which is the result found after applying the proposed zero DCE technique, the lighting looks very much balanced and visually appealing. So this technique definitely deserves more attention from us. So let's look at the network in further detail. This is a high-level picture of the proposed zero DCE network. One dark image is provided as input to a deep curve estimation network, which is a convolutional neural network. Then the authors came up with an image transformation equation like this. It's a quadratic equation. ALE means light enhancement. So this equation is used to transform the image, where X is the pixel value, IX is the input image, and alpha is like a learning rate, which can be trained. Okay, so it's like a trainable parameter. So in this equation, alpha is only image specific. Then we can get higher order curve parameters through multiple iterations like this. Here, multiple iterations are considered, and alpha became alpha. Here, alpha depends on the number of iterations too. But still, the curve parameter is like a global variable that applies to all pixels, irrespective of local brightness. So it may result in poor enhancement for some images. Thus, the parameter alpha n is made pixel specific here. So here you can see that it depends on every pixel. So we will get different values for different pixels. Also, alpha is RGB channel specific. I mean, it will estimate alpha for all 3 channels separately. So in this way, alpha becomes a highly adaptive parameter. Okay, now let's go back to the network. The deep curve estimation network generates the curve parameter maps here. So these are basically alpha values for every pixels and for every channels. And then this image transformation equation is used to transform the image. So this is an enhanced version after the first iteration, and then it continues. In the second iteration, the input image is the output of the previous iteration. So in this way, in every iteration, we have some incremental improvement. So here you can see that some pixel level transformation curves are shown. So figure C shows this one. C shows some higher order curves, which considers 4 iteration. So however, in these graphs, alpha is same for each pixel, but here in the actual network, alpha was pixel specific. So that means we might get different curves for different pixels. So let's look at this visually a little bit here. Pixel-wise estimated curve parameter maps. So for this input image, the estimated curve parameters of all 3 channels are shown as heat maps here. Alpha value ranges between 0 to 1. You can see that alpha value for the pixels in the dark region is higher or close to 1, while the brighter pixels, for the brighter pixels here, alpha value is small, which is close to 0. So thus the final image is seen to reveal the contents in the dark region while preserving the bright regions. Another important aspect of the proposed method is the customized loss functions. They used 4 loss functions in the process, which will be discussed by my group partner Atik next. So Atik, please start your presentation.
Thank you, Zobaer. Now I'm going to present the loss functions that are used in this study. So there are 4 loss functions that are used in these studies, and they are called non-reference loss functions because they do not require any pair image for the loss calculation. And the final loss function consists of all these 4 losses. So the loss functions are called spatial consistency loss, exposure control loss, and then we have color control loss and the illumination smoothness loss. So the total loss is the summation of all these loss, and the last 2 losses have some weight function to assign some custom weight to them. Next, we talk about the loss functions in details, and we have put the code for this loss function so that it's easier to understand. So the spatial consistency loss encourages a spatial coherence of the enhanced image. It uses 4 kernels. You can see 4 kernels here, which are up, down, left, and right. So the inputs and outputs are convolved with the kernels, which are convolved here. And then we take the square distance. Then we ultimately take all the distance to calculate the final distance of this loss output. The next loss is called exposure control loss. To restrain under or overexposed regions, exposure control loss is used. Here we take the mean of outputs and we pass it through an average pooling, and then we calculate the square distance. Here we have a threshold value, which is 0.6 as suggested in the paper. Next, we have color consistency loss. This loss is used to correct the potential color deviations in the enhanced image. Here, first we calculate the mean of each channel. So we first calculate in the code the mean of each channel, and then we calculate the square distance between each channel. Then we calculate the root square distance of all the channels together to get the final loss. The next loss is called illumination smoothness loss. And this loss is used to preserve the monotonic relations between neighboring pixels. In this loss, we perform the horizontal and vertical gradients for the total number of iterations. So the ultimate gradients are divided by the total number of iterations. Next, we're gonna see some output from our dataset. For that, I'm gonna share the output from our code because we applied this method on some of our test dataset to see how well it does on our dataset. So I'm gonna share the code that we have done for this project. So these are the test dataset that we applied for from our own images. These are not the images that were trained on. But we see that in some images, the outputs are very good. It does a good job to enlighten the image, but in some cases, it introduced some artifacts or some noise in the image, or sometimes it was overexposed. Like in this image, the image was enhanced, but in the next image, we can see there are some artifacts on the sky, or there was some noise in the image. And then we applied this architecture to our machinery data, where this is the original image and like the ground truth, and this is the darkened image, and this is the enhanced output. So we can see this network could enhance the image, but it also introduced some noise. But sometimes it did a good job, like in this image, it was close to the original image, but it was still a bit overexposed. So in conclusion, we can summarize that this method can enhance image and enlighten image, but sometimes it's not very generalized. That's why we have some noisy output sometimes, or sometimes it's very overexposed. But nevertheless, these images are our own test data, and the model was not trained on this data. So still it does a good job to enhance the image. Okay, so now back to the slides again. Next, we have our ablation study. So in the ablation study, first we visualize the contribution and effects of each loss. In image B, the output is used for, it's from all the losses together that were suggested in the 0DC paper, but in the other outputs, the losses are from each single loss. So we can see that in the output here, the sky is kind of underexposed. Sometimes the background foreground is underexposed or the color changed. So when you are using all the losses together, the network performs the most with the best accuracy. Then we see effect of parameter settings for the network. The effect of parameters in 0DC is evaluated by varying the depth, width, and the iteration of the network. So we can see that when the network is 732.8, which is the depth and the width and the number of iteration of the network, and 732.16, it produces the most visually pleasing output. And the other images which are not that deep, it is kind of underexposed. Next, we have qualitative comparison. In qualitative comparison, it is conducted on various subjects by asking them to rate the outputs of different methods based on the visual quality. So the indexes are user study and perceptual index that are presented in the table to show the effectiveness of different methods on various datasets. And in most cases, we see that 0DC here in most cases obtained the best performing results. And then next we have quantitative comparison, which are PSNR, SSIM, and MAE, mean square error, that are used with the reference images. And we see in most cases, in all of the cases, 0DC obtains the best output. And we, in the next table, in the second table, we have runtime comparison, where we can see 0DC has a very significantly lower runtime than the other methods. So that, and also we have future study, also other application of this paper, which can be applied to face detection. So 0DC can be expanded to face detection. And in the first image, where we can see the image is very dark, it can only identify a few images, like 4 images in this image. But when you enhance the image by 0DC, we can see that there are more faces identified in the brightened image. So it can also be applied to face detection. So that's mostly about this paper. These are the times we made to generate these slides and to make this presentation. And thank you all for listening to our presentation. If you guys have any questions, please feel free to ask any question. Thank you.